So let me talk about the standard electrode potential. This is what the textbook said is the standard electrode potential. But the one that I want you to remember is this is the same thing that people are telling you, that standard reduction potential. And I took out some numbers from the exam reference sheet that is shown up here. And then if you look at this ugly looking big table, so you remember the first page of the reference sheet, and this is, although it's very small, if you blow it up, that's a standard electrode potential. I don't know whether they are trying to be ambiguous here, but if you look at that, anything that here is receiving electrons to be reduced. So this is all reduction potential. So it's better for you to see the value that you see in the standard electrode potential is essentially what they are trying to meant to be here. This is the electrode standard reduction potential. So make sure that you understand it. And then I like to do something like a little bit, less scientific, but I like to learn how to use this equation in a way that I am going to, you see that there's different reactions. Ag get reduced to the Ag0. Copper is, ions are reduced, receiving 2 electrons, they're coppers. So yeah, they are getting those. And so essentially electrochemistry, they are competing for the electrons. And this one essentially shows the rank. Who is going to win in the competition of getting the electron? What that means is there is another one, the other side is going to lose their electron. And this is going to be the wins. This one wins. Okay? So the higher in the rank of this value, you are the one who's going to win. So if I choose the situation where the copper and the most common one is actually zinc, for example here, who's going to win? Yeah, this is going to win. So what that means is I'm going to keep the way as it is, and this will be the essentially reduced. Okay, so then let me kind of take it a different way. Then who's going to lose? This is going to be lose. So what that means is you are going to have this reaction happening the other way, which is oxidation will going to happen, and this is a reduction potential. Then you have to change it into an oxidation way. So what am I going to do here is now spontaneous reaction that you will see here now will be understood by looking at it. Okay, I'm going to take this winner. And then I'm going to take this loser, and then I'm going to switch this one around. So therefore, this reaction, I'm going to write it as it is. So it's good for you to remember to write copper 2 plus, 2 electrons. Yeah, they are the one who's going to keep it as it is, which is a reduction. And then the zinc will be happening the other way. Zinc will be oxidized by losing 2 electrons and generating zinc 2 plus. In this case, if I tally up, they are the one who's going to get rid of, and then you will see the net reaction will be copper 2 plus, zinc metal is now changed into copper metal and zinc 2 plus. And what's my electrode standard cell potential? That will be, I'm using the notation as reduction plus oxidation. So this is some people use this notation, some people do not use the other way, but I like to use this way. And then what I mean is this one is a reduction potential, right? But if you think about this oxidation, so I'm going to write this value in blue, and then E oxidation from this value is the negative E reduction. So therefore, oxidation for the zinc oxidation is going to be plus 0.76. Okay, and whereas this is one that I'm still can use the dark black colors to be black. Okay, so then this one is actually reduction that you see here. Oh, let's know what happened here. This is going to be E reduction, right? So therefore, in this cell, you will see that, okay, copper keep the reduction as it is, and then zinc, you have to flip it so that the potential value is changing the sign, and this one is 1.10 volts. And then what you also see the most, this is actually quite important for you to figure this one out, because now you see this, and you can really define this as what is called a Nernst equation, and then something called the Q value here will be Cu2 plus on your left hand side, right? So it goes to the bottom, and the zinc 2 plus goes to the top. Okay, so that's how the Q is defined, and I have shown an example how the Nernst equation can be calculated using Electrochemistry 003 version of this crash course. This time I'm going to actually tackle a little bit more challenging problem, which is this is probably conceptually much more difficult. So think about this way. I have a solution that this is a copper, right? And then you have a copper 2 plus, but this is a concentration of 10 molar, okay? And then the other one, you dip the copper metal, but your copper concentration here is 0.1 molar, 0.1 molar. So this is a lower concentration, and this is a higher concentration. And then you are going to connect this to line, right? And then depending on which way they flow, you can make this connection, generate some the current flowing in. So what kind of change should it happen? So let's think about it, right? So you have this higher concentration, and this is lower concentration. So this is a logical for you to say, okay, the concentration, because it's lower, I'm going to bump up the concentration. There's a motivation for this one to get oxidized here. So this side is going to be happening this way by saying, okay, so this side, copper metal is going to be copper 2 plus 0.1 molar concentration with 2 electrons. Because it's a lower concentration, so this is much more motivation to do it so. And so by doing so, there's an electron is escaping from this side. Right? The 2 electrons are coming out, and eventually they're going to flow this way. So electrons are flowing, electrons are flowing. When you have these electrons coming in, this higher concentration is actually going to deposit from Cu 2 plus 10 molar will be deposited into by taking the electron from the other side will be a Cu metal. Okay, so what that means is this side is going to the copper metal will be deposited more, and this way they're going to lose a copper solid into a form of the copper 2 plus. So I can write this equation in this way. Mm-hmm. So although it's the same one, I can make a logical guess that this is an oxidation, this is a reduction, right? Oh, and by the way, I also said that everyone in the session say I'm pretty sure that Kathleen talked about ox versus red cat. So has she talked about in the lectures? This is a kind of the common cheating way to remember which is a cathode. Cathode is a reduction, and anode is an oxidation. Can anyone type some comments in the chatting box? Have you guys heard about this? The ox, red cat? I think I like to remember the red cat. Have you heard about red cat? Is there anyone hear me? Have you heard about red cat? If say no, I'm fine with that. So if not, please remember the way that you can remember is red cat, and I hope you guys are listening to me. Otherwise, I'm gonna stop. Okay, so if you guys do not type any words in 10 seconds, I am going to stop this session. Okay, 3, 9. You never heard about it. Okay, thank you. So I know you guys are tired, but I am tired. I'm taking this extra hours, and please let's get involved more. You never heard about before, but does it make sense to you now? You see the red cat. Red cat is something not scientific, but is a way to memorize. Cathode means a reduction reaction. Right? Anode means an oxidation reaction. Please remember that, and that because electrochemist is a very kind of the old chemistry that they change the notation for many times, and sometimes it's very confusing. So I hope you guys remember that. Anyway, okay. So I'm going to write the reduction reaction, which is a cathode side. So this is a reduction. So this is actually cathode side. And this is an oxidation, which is an anode side. Okay, so this is a reduction, and this is an oxidation. And I am going to write the reduction happens. So the reduction happened here. Copper, 2 plus, high concentration, will get 2 electrons and becomes copper. And then oxidation means copper metal itself going to be copper 2 plus dissolving into the low concentration containers and 2 electrons. So this is in a way a little bit more complicated, but it should happen this way. And then if you add it up, the net reaction that you will see will be copper 2 plus 10 molar. And actually the coppers are gone too. So the equation becomes pretty simple. Copper 2 plus 0.1 millimolar. Okay, so this form is worthwhile for me to spend the time to derive it, because I am going to essentially calculate the Nernst equation using this notation here. Okay, so the Nernst equation is our ability to solve this equation shown up here, and the case shown up there will be an equation that I already write it before. The copper 2 plus 10 molar is a copper 2 plus 0.1 molar. Okay. So if you have that, what is my cell potential? Is once again is a reduction potential plus oxidation potential. And if I look at my reduction potential, actually, let me go over and look at it. That's what's my reduction potential? That's plus 0.34. What's my oxidation potential? I guess the same number, opposite sign. So you have a standard cell electrode potential is actually 0 for this. The cell with a different, same kind of component, just having a different concentration. Okay. But now, having said that, what is a Q here? And Q in this one is because the way that is written is a copper 2 plus high concentration and copper 2 plus low concentration. So that means 10 molar, 0.1 molar. Okay. So in a way, 1 over 100. Okay, so therefore, although there is no standard cell electrode potential being generated because these are chemically identical, because of the concentration differences, you still generate some electrode potential, which is now 0 minus NF RT ln 1 over 100. Okay, so ln cube. So that's the value. And then here I wanted to show it to you. What do you mean by this F? I think that I mentioned to you from the other session as well. This is worthwhile for me to understand that. F is a Faraday constant. is almost like a gas constant for the gas law. It's so important. The Faraday constant is being used in many places. And the Faraday constant is nothing but it is a charges for electron when you have 1 moles of it. So I actually 96500 Coulomb for 1 mole of electrons. And you don't have to remember this number like I do. If you look at that here, and let's go up. So do you see the 1F? This F is a Faraday constant, 96500. That's what I want to use. You don't have time to write them all. So 965 is a good enough number for Coulomb when you have 1 moles of electron. So that's the number. Essentially, it's just a collection of 1 mole, 1 Avogadro's number of electrons, and you will develop these charges. And then what is my N? N here is, I said, that's the number of electrons involved. So you need to really write the half reactions. And you guys can see here, there's 2 electrons that cancel out each other. So between this reaction, that the way that it is written, the transaction of electron is essentially 2 moles, right? So therefore, I ended up writing that equation now. E cell is minus 2 96500 and then 8.314, and then temperature is a room temperature 298 Kelvin, and natural log 1/100. Okay, so that's a volt. Okay, I didn't have a time to calculate this one, but you can find out. This is a negative number, right? So therefore, you have a positive some sort of the voltage numbers, and so it is possible to generate some electrical potential differences, chemically the same, but you have essentially a difference in the chemical concentration. So this is a little bit more deeper end, and then I'll